Okay, so today I'm covering section 1.3 in our Glencoe Pre-Calculus book. It's a pretty lengthy lesson, so I have decided to break it up, and the first section is going to cover basically just limits to determine the continuity of a function, and then part B will cover the intermediate value theorem and end behavior. So if you need help with just end behavior, you want to go look at part B. So first and foremost, let's talk about continuous functions. Now, the most important thing you want to remember is not to overthink it. Just like you can imagine, a graph is continuous if you can draw it without lifting up your pencil. So, if I start my pencil here, I can trace my graph without ever picking up my pencil. That means it's a continuous function. If we look up here at this graph, if I trace the graph, I would have to pick up my pencil to get to the next point, or the next point, or the next point. So this is not a continuous function. But what we're going to work on today is using the concept of limits to prove algebraically that a function is continuous. So we're going to use the picture, but we're also going to use algebra to support our concepts. Okay, so as we start that, let's talk about what a limit is. And just like you have speed limits outside and you can't drive, not supposed to drive over the speed limit, you can get as close and close as you want to, but you shouldn't go over it. Okay? We have a limit of a function if, no matter which side of the function you come from, you get closer and closer to that point. Now, the easiest way to think about that, I believe, is to use your fingers to trace the function. So if I'm coming from the left side of my function, I trace with my finger down to a point, and I use my right hand from the other side and trace with my finger to that point. And if my fingers meet in the same place, then I will have a limit. Okay? Now that's actually just one part of our algebraic proof for continuity, but it is something we will be using. Now, before we go on, let's take a look at discontinuous functions, okay? Just like our fingers, if we start our left finger following this part of my graph and my right finger following this part of the graph at the same time, you can hopefully see that they will never meet each other, okay? The left side of my graph is going down to negative infinity. The right side of my graph is going up to positive infinity. So we call this infinite discontinuity. That's the example of that. Now if I trace on this graph, I'm tracing on the left side, okay? To get to the right side, I have to jump to get to the right side. So this is called jump discontinuity. And then the last one we have is it still has a limit because as I approach from the left and I approach from the right, I do get closer and closer to this point, but the problem is my function is not defined at that point. It has been removed at that one specific spot, so we call it removable discontinuity. Okay? So, again, the easiest thing, I believe, for you to decide whether or not something is continuous is to trace that graph with your fingers. Okay? Now, as we go forth, we got to talk about algebraically how do we prove that. All right, we have three conditions, and as it says, you must meet all three conditions for a function to be continuous. Must meet all three conditions. So if I have a function and I'm drawing my function, all right, and I can go from one end of the graph without the other, it's continuous. Okay? All of my function is defined and my limits will take place. And we're going to talk about that now algebraically. Keep in mind, I'm going to put a little hole in my graph right here. That was a little bit bigger than I expected. However, so we come here and we have a hole. Okay? When we're talking about continuity, okay, keep in mind at this particular point the function is not continuous. But if I move my c to over here, okay, then my graph is continuous. So it is very specific to the point at which we're looking on the function. So let's go do some examples. First and foremost, we have determine whether f of x equals 2x squared minus 3x minus 1 is continuous at x equal 2. Justify using the continuity test. So the first part they want us to do is, does the function exist? So I'm going to go plug in 2. That gives me 2 times the quantity of 2 squared minus 3 times 2 minus 1. And when I simplify that, I find out that f of 2 is equal to 1. Now, does the limit of 2 exist? Okay, a couple of things you're doing. What we were trying to do, as I showed you on this graph right here, okay, we happen to be, for this particular problem, right here. And we want to know what happens as we get closer and closer to 2 on both sides. So we start off always 1/10 away, and then we, on both sides, 1/10 away, and then we go to 100th away, and then we go to 1,000th away. So hopefully you can see that that means we're getting closer and closer to 2. So we're going to put those numbers, these values, into our function, okay? And we're going to see what happens as we do that. Now, you can put that into the table, plug them into the function, but to move along, when you do that, you get these values for your y, or f of x. All right, so when you do that, we have f of x, in this case, okay, 0.52, 0.95, 0.995 is getting closer to the number 1. 1.52, 1.05, 1.005, my function is getting closer to 1 again, and the value of my function is 1. However, when we have that the function is approaching the same number no matter which direction that I go, then I say that the limit as x approaches 2 of my function is equal to 1. So it does exist. Its value is 1. And since the limit as x approaches 2 of f of x is 1, and the value of the function is 1, then I can say that my function is continuous. Therefore, f of x is continuous. Okay, let's go look at some more examples. So we have determine whether each function is continuous at x equal to 0. Justify using the continuity test. So I'm looking for the value when x is equal to 0. So first step, what is the value of the function at 0? F of x, plug in 0 for x, and we get 0. Number 2, we're looking for the limit as x approaches 0 of the function. And we're trying to find out if it exists. So I'm going to draw the table vertically this time. We've got our x, we have our f of x, and as you saw, every single time we're going to find 3 numbers on one side of 0, and we're going to find 3 numbers on the other side of 0. Okay, and of course, 1/10 of a way, negative -0.1 or -0.1, negative -0.01, -0.01, and negative -0.001, and -0.001. So when we cube each of those numbers, we're going to get 1, 2, 3, 1, 2, 3, 4, 5, because I'm just counting my decimal places. And this time I'm going to have 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course at 0, we already calculated it was 0. And the only thing that's going to change here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, and 1, 2, 3. So I'm looking at these numbers. Does f of x go towards the same number as these do? Okay, these numbers, that's big, that's smaller, that's even smaller. Actually, take that back because on a number line, of course, this number is the smallest. So these are getting bigger and they're getting closer to 0. These numbers are getting smaller and they're getting closer to 0. So we say the limit of our function limit of as x approaches 0 of f of x is 0. Okay? And our third condition says, does the limit as x approaches 0 of f of x equal f of 0? Okay, that's what we're trying to figure out, and it does. So, to answer the question, we say, therefore, f of x is continuous at x equals 0. And that can help you if you want to go put that in your calculator. You can look at it and hopefully, or remember from your library functions what that looks like. But that general shape is looking like this. It is that's our cubic function, so it's continuous. All right, let's look at another example. We have f of x equals 1 over x if x is less than 0, and x if x is greater than or equal to 0. So we have a piecewise function here. The first step, again, is f of 0. And if x equals 0, I'm going to use the bottom one. So it's equal to 0. That works. All right, the second one, we're looking for the limit as x approaches 0 of f of x. And we're looking to see if it exists. So we're going to go do a table, just like we did. We're going to have the same x values. This is my x, my f of x, 3, and then I had 0, and then 1, 2, 3. So I have the same numbers as we said, negative 1/10, negative 100th, negative 1,000th, 1,000th, 100th, and 1/10th. Now the difference here is we have a piecewise function. So when we put in our x value, we have to go look at which of these pieces to use. These values are less than 0 right here. All those values are less than 0, so that means I'm going to use that rule to calculate. And on the flip side, all these values are greater than 0, so I'm going to use that part of the function to find the value. So 1 over negative 1/10 is, of course, negative 10. 1 over negative 100th is negative 100. 1 over negative 1,000th is negative 1,000. Now for 0, which one do we use? What we just said, so it's 0. And then here, of course, the bottom ones, we're using the bottom ones, and x equals y, or f of x. So we just get to write that same value. So we're looking at these numbers. Are they getting smaller and smaller, closer to 0? They are. These y values are getting closer to 0. On the flip side, these y values, the numbers are getting larger, but with our negative sign, that means these are actually going towards negative infinity. So since these two are not going to the same place, we say the limit does not exist. That therefore f of x is not continuous. Okay. Now, one of the things that I wanted to show with this, we're really using the Inspire a lot, so I wanted to give you an idea of how easy this was to look at. So we're going to look at the graph of this just to help solidify our understanding of it. Okay? We have a piecewise function, and on your Inspire, if you're on a graphing page within a document, or you don't, it can be without a document, but I like to work in documents. So I'm going to put a piecewise function. So I go to the left, the button just to the left of 9 that allows me to pick my piecewise template. I click on it, I press enter, and now I'm going to type in my function. Now the top part was 1 over x. Again, let's pull up my fraction template, highlight it, press enter, and I'm going to type 1 over x. And I believe that was for x. Our less than is right here above the equals, so we hit control equals less than 0. And then I go to the bottom one. Of course, it was equal to x when x was control equals greater than or equal to 0. And once we hit enter, it will actually graph for us. Now, the other thing I want to point out real quick, in case you, and the same thing applies on the 83 and the 84, is to get to your table. Well, a table set is different on the 83, but for Inspire, to pull up our table is Control T. And what I want to do here is I want to put in these values so that I can check them against my table. Then I click on Menu, and then I hit number 2 for Table and number 5 for Edit Settings. And instead of worrying about the table start and the table step, I'm going to click on here and get Ask. And that allows me to put in the numbers that I want for x. So we had negative zero point 0.1, negative 0.01, negative 0.001, then we had 0, and we had 0.001, zero point zero 0.01, and zero point 0.1. Okay, and then you can go back up and look. Those were the values that we had on our table. So that's a quick way to look at that. Enter that if you don't want to put all the numbers in or figure them out by hand. Control T takes your table off. But again, we were looking at our function at x equal to 0, which is this point here. And as we saw, when we came from the left side of 0, our numbers were getting larger with a negative sign, meaning they were going to negative infinity. And as we came from the the right side of our graph, we got closer and closer to 0. So that's just a good visual to confirm what we were doing algebraically. All right, let's look at two more. Determine whether each function is continuous at the given x values. Justify using the continuity test. If it's discontinuous, identify the type of discontinuity as infinite, jump, or removable. So we are looking for the function at x equal to negative 3. So the first thing, we plug in f of negative 3. Now which one do I use? This is the one for x is equal to negative 3. So I'm going to say 2 minus negative 3. And I'm going to get that f of negative 3 equals 5. All right, second, we look at the limit. As x approaches negative 3 of my function. And I'm looking to see if it exists. So let's go do our table. We've got x, we've got f of x, and remember we have 3 values before, 1, 2, 3, with a negative 3, and we have 3 values after. All right, and remember that we started with a tenth, and these were our smaller numbers. So to go smaller, a tenth of a way is actually negative 3.1. And then on the other side is going to be negative 2.99, because this number is closer to 0 than that number. So then we have two decimal places, 0.001, negative 2.99, negative 3.001, and negative 2.999. Now, plug in those values, okay? Keep in mind, we have a piecewise function, so we're going to have some different things. These numbers right here, we just talked about, are those bigger or smaller? They are bigger than negative 3 because they are to the right on the number line. So they are greater than negative 3. That means we're going to be using this expression to evaluate them. And these numbers are less than negative 3. So we're going to be using that expression. So plugging those numbers in, you get, and if you want to pause right here to plug them and put them on your table and then check yourself. 5.1, 5.01, 5.001. Of course, we got 5 over there on our graph. Just makes it easier for us to look at. Negative 10.997, negative 10.97, and negative 10.7. Now, these numbers, are they getting closer and closer to 5? They are. They're getting closer and closer to 5. These numbers are getting closer and closer to negative 11. Okay? So, do they both approach the same number? The answer is no, so we say that our limit does not exist. Therefore, f of x is not continuous at x equals negative 3. Okay, they also asked us to identify the type of discontinuity. So hopefully you can see neither of these numbers is approaching infinity, so it's not going to be infinity. And remember, removable was if they both approached the same number. So that leaves us with this being an example of jump discontinuity. I can't spell. Discontinuity. All right. One more example, and then we're going to stop with discontinuity. All right. We have f of x equals x plus 3 over x squared minus 9 at x equals negative 3 and x equals 3. So we actually have two different cases that we're looking at here. This is one, and this is another. So let's go look at the first one. Excuse me, we go plug in f of negative 3. And when you plug in f of negative 3, you get 0 over 0. And of course, we remember that division by 0 is undefined. So we say that the value, basically the function, is not defined at negative 3. Now, that's enough to tell us that it is not continuous. F of x is not continuous. However, it asked us to tell it what kind of discontinuity it had. So if we're going to find out what kind of discontinuity, we need to make our table. And so we have our x and our f of x. I'm not dying, I'm really okay. 1, 2, 3. We're looking at negative 3 here. And 1, 2, 3. And remember our numbers we had were negative 3.1, negative 3.01, negative 3.001, negative 2.999, negative 2.99, and negative 2.9. Okay, so I am going to go put those into my calculator, and I think I've actually already done it, so we can look at it. When you have more than one page in your TI Inspire, you can hit Control and the left arrow to go between the pages. So here is my function, and I was looking at the graph, and here is my x equal to negative 3, that vertical line. So I'm looking to see if the graph is continuous at that point. Now it looks continuous. So if it looks continuous, but we just figured out the value is not defined, hopefully that's enough to tell you that your function is not defined. I mean, excuse me, what kind of discontinuity it is. It looks continuous, but the function is not defined, means we have removable discontinuity. Okay, and in case you can't tell, let's go look what the table would look like. So I'm going to hit Control T to bring up my table, and I'm going to hit Menu, and then number 2 for table, number 5 for settings, go to independent, change it to ask, say OK, and I'm going to put in the numbers. So we had negative 3.1, negative 3.01, negative 3.001, negative 3, negative 2.999, negative 2.99, and negative 2.9. So when you look at these numbers, look at them as we have, this is negative 0.169492, so negative 0.166. And so you can see these numbers are actually approaching the same number. So that's a great example of what you have when you have removable discontinuity, okay? So in the interest of time, I'm going to go back to, and I'm just going to say that we saw these numbers. This was negative 0.166, and this was negative 0.166, and they were both going to that number. Of course, this was undefined in our table. Okay, so let's go look at the second one, and if you remember from our graph, that means we're looking at this part of the function. Remember on an Inspire, if your label is out of the way, you can go click on it and move it somewhere so it doesn't disturb your picture. But we put in the graph of x equal to 3, so hopefully you can tell clearly from the picture that it is not going to be continuous at that point, and that it's going to have infinite discontinuity. But let's go fill in the algebra so you can make sure. Let's box this answer so we know that we finished that part. So on the second one, or still the first one there, number 1, f of 3. We have 6 on the top, we have 0 on the bottom, so we still have f of 3 being undefined. So we're going to go in and say again, f of x is not continuous. And from our picture, I think we can all agree that it is infinite discontinuity, right? But my table, just in case some people want to know what our table would look like, we're going to go look at that, and then we'll stop. So we have, if you're good with that, you can stop the video now. If you want to look at the table, just to confirm or get some more practice of what we've been doing, this is negative 3 and, excuse me, positive 3, that's what we're talking about, and it is undefined. So my smaller number this time is going to be 2.9 because I'm on the positive. 2.99, 2.999, 3.999, 3.99, and 3.9. Alright, and again, let's go back and we're going to hit Control T. There's my table. I'm going to hit Menu. Up there's my menu, what I'm choosing from. I'm going to choose 2 for table. It didn't like that. 2 for table. Okay, come on. There we go. And 5 for settings. Click on ask for the independent variable and click OK. And let's go put in 2.9, 2.99, 2.999, 3, 3.9, no, sorry, 3.001, 3.01, and 3.1. So, as I go to 3, what are my numbers getting closer to? They're getting bigger and bigger because they're positive numbers. So on my table, this one was, I think it was like 10, 100, 1,000. So those numbers are getting bigger, positive infinity. What happened on the left side? Oop, they didn't want me to go up that way. Negative 10, negative 100, negative 1,000. Okay? So we had negative 10, negative 100, negative 1,000, and those numbers were getting bigger and bigger, negatively speaking. So that was negative infinity. So again, they were going both towards infinity. Those numbers were getting, the numbers themselves were getting larger. So that sums up continuity. We confirmed it with our picture. We proved it with our algebra. And that stops the lesson. Go to part B if you want to hear about end behavior and the intermediate value theorem.